Hello, my name is Dave Melton. My friends call me Crazy Dave, and the reason is occasionally I have a bright idea. In fact, it's a flash of inspiration, but it doesn't last long. One of my simple ideas was an automatic fire extinguisher system that comprises a simple plastic tube that bursts when it gets hot. This can be employed inside electrical equipment, engine compartments, machines, anywhere where there could be an overheat. Now, as I'm making automatic fire extinguishers, I started thinking about, why do we have fires? What causes fires? Where do fires come from? Now, a fire officer once told me there are three major causes of fire. That's men, women and children. Somebody has done something silly. Now, this may be true in general life. In industry, we lock everyone out. We only allow in our staff, who should be highly trained, not to light accidental fires, mind you, with limited success. So why do fires still happen? They must happen because of energy. If there's nobody there, what's causing the energy? Typically, equipment is run on electrical current. Now, electricity is a strange beast. It's very closely related to magnetism. Energy and electricity and magnetism can make movement. I have a simple experiment here, which is a small magnet, 1.5 volts, a piece of bent wire and a couple of magnets. Now that creates rotation. Okay, that is basically an electric motor. It's all there is to it. Now think about it. If you intended this to happen, it would be inside an electric motor in a controlled environment. But anywhere there's electricity, non-ferrous materials and magnetism, you can have movement. So small offcuts of metal or swarf can be made to move about because energy and magnetism create electricity. Now the energy can be very simple. What I have here is a copper tube with some holes in, and I've got two pieces of material exactly the same diameter. One's a bit bigger than the other to make the weights the same. We've got the same hole in it. If I drop this piece of metal into the tube, it falls straight out of the bottom, exactly as you would expect. Now this other piece of material is in fact a magnet, but it doesn't fit in there. It's the same diameter. When I drop this in, it only comes out very, very slowly. The reason for this is the magnet going past the copper generates electricity, the exact reverse of the movement caused by electricity and magnetism. This is copper and movement making electricity, and electricity causes it to stop. There are so many applications where this can have an effect. The mystery of fire is not a mystery, it's electricity. Now, magnets do all sorts of strange things. I have a small magnet here and a 2-pence piece and a piece of wood. No expense spared in my laboratory. I've completely destroyed a coat hanger to make this. If I take the magnet to one end, the penny talks to the coat hanger. When I move it back, it stays with it. We start again. Now this is a coat hanger, this is a penny, and pennies don't talk to coat hangers, but they do talk to magnets. They can see magnetism, can see straight through wood and plastic, non-ferrous materials. But remember, the penny doesn't talk to the coat hanger. But if it's in the magnetic field, it does. Because the magnet is inducing magnetism into the coat hanger. If I take it far enough away, the penny drops out of the magnetic field. The coat hanger still doesn't talk to the penny.
The principles of electromagnetism were first sorted out by my hero Michael Faraday, so I've tried to reconstruct his original experiment. How to make a pie dish electric motor. All you need is a 12-volt power supply, a tinfoil pie dish and a piece of wire, plus a small quantity of water with some salt in it. As you can see, electricity and magnetism can do some strange and unexpected things.
Now, Newton's law suggests that every force must have an equal and opposite force to oppose it. So what I have here is a small piece of truncheon with a spacer under one end to make a slight incline. So when I roll the ball down, it gains energy. Now this force will hit that, will hit that, will hit that, and in theory push this off the end with the same energy that comes into it. But things are not always quite as you expect. You ready? This is exciting. As you can see, there's considerably more force. The reason is there's a magnet there. So as this rolls down, the ball hits the magnet and the impulse knocks the end ball off.
You will notice that only the first and the last ball moves. The centre ones remain stationary. This perfectly describes how electricity flows through a cable. It comes in at one end, out at the other, and it's stationary in the centre. About 20 years ago, we demonstrated this system on the BBC Top Gear programme.
The same system can be used in any electrical wiring installation, either in buildings or behind a car's instrument panel. A localised fire is quickly extinguished. The pressure gauge indicates a discharge has occurred unless an audible alarm or flashing light on the dash is fitted as well. But that's all very well for a relatively small underbonnet fire. What happens in an accident if you're trapped in the car, perhaps unconscious, in a pool of burning petrol? Well, we've got that pool of burning petrol, which my assistant is going to set a match to. This test car is equipped with another cylinder and a line running round the underside of the engine bay. So let's see what happens. The device certainly seems to work very effectively indeed. It'll be available on the aftermarket, but I think it's too important to leave to somebody to decide to fit to their car. It's something all manufacturers should be fitting as standard. And just to show, this rather singed Vauxhall Cavalier still works.
Well, let me just repeat Chris's warning. Please don't try out those experiments for yourself because, of course, they can be very dangerous. That apparently anonymous car park was at the fire extinguisher factory itself, and we had lots of skilled people standing by just out of sight in case something went wrong.